Organizers, it's a very good opportunity given to me to start this conference. First of all, let me congratulate WCOC organizers for successfully conducting this platform and giving organic chemists this platform so that they can interact with each other and their ideas can be shared. Thank you so much for giving this opportunity to all the organizers, and my regards to all esteemed audience. So I'm going to start.
SGT University from India. As we begin the presentation, let me take a moment to introduce her biography. Nutan Sharma is a faculty member at SGT University, India, with research experience in organic and green chemistry. Her work encompasses the eco-friendly synthesis of nitrogen-containing heterocycles using the principles of green chemistry. She has decided to advertise in sustainable chemical methodologies that reduce environmental impact while maintaining efficiency, innovation in drug and material development. Now I would like to introduce our third keynote speaker, Nutan Sharma. Nutan Sharma, please start your presentation.
Everyone, am I audible to you all?
Please unmute your mic. Your voice is not audible. Hello? Your voice is not audible. No, ma'am. Please check your earphones. Headset.
Am I audible now?
Yes.
And I have checked my. Is my video available to all?
No, your voice is not audible.
My video?
Sorry?
Is my camera?
Yes.
See me, right?
Hello? Please remove your earphones and continue your presentation. Maybe it is
My headphones, but
sorry?
just a minute.
Am I audible right now?
Yes, you will please continue your presentation.
Okay. And is my PPT visible to all?
Yes, yes.
Okay. Sorry for the interruption, and good afternoon to you all. Myself, Dr. Nutan Sharma. I'm an associate professor in the Department of Chemistry in the Faculty of Applied and Basic Sciences in SGT University program. Program is called the Cyber Hub of India.
Professor Sunita, your voice is not clear. Sorry to interrupt. Not audible. I think your earphones have some problem. Hello?
Am I audible right now?
Yes.
Okay. So first I would like to introduce my university to you all. Actually, SGT University is situated in Gurugram. It's spread in 80 acres of area. The university is having all the courses. Uh, the university is NAC A grade accredited institution. It's located in Gurugram and it has a lush green campus which is spread in 80 acres. It has 18 faculties. You name the faculty and the university is having all the courses other than the very renowned medical and dental colleges, which is a very well established and an old college in India. So my talk is related to green chemistry. So first I would like to emphasize why green chemistry is so important and why everybody in the world wants to perform it and wants to talk about it. Generally, the chemistry that organic chemists they perform, it involves the hazardous chemicals, solvents, and reactants, ligands, catalysts. So chemistry will be performed, is being performed, and it's a never-ending phenomenon in the world of drug discovery. So what we can do is we can bypass or eliminate, or if we can reduce the hazards related to the organic chemistry. So that is why the term green chemistry matters here, because the traditional chemical processes they generate the massive amount of waste when we do the organic chemistry, and it sometimes weighs in 100 kilos of the waste product per amount of drug synthesized or the active pharmaceutical ingredient synthesized. So when we perform the green chemistry, it eliminates the pollution at the molecular level, and which is the need of the hour, because everybody is so much concerned about environment right now. The various physical phenomenon happening in the nature, they are getting affected by these hazardous chemicals, solvents, and the waste which is generated every day. So what is green chemistry all about? There are 12 principles of green chemistry. It involves the methods which are sustainable in nature. It involves the methods which are energy efficient. Minimum chemical waste is involved. The benign solvents, or we can say is the eco-friendly solvents which are used. And the isolation processes in organic chemistry, which basically involves the column chromatography, they can be avoided. And the safer catalysts and reagents should be employed so that the chemical processes can be made green. So first, we would see what are the different green chemistry techniques which are right now in demand. The first is very simplest and very wide known technique. It's called the grindstone technique, which is nowadays utilized very much. It involves the bypassing of the hazardous solvents at all, and that simply involves the grinding of the two components or the three components. It can be a multi-component approach also, which involves the cyclocondensation reaction. Here the wheel represents the various type of reactions which can be performed by simpling these grindstone technologies. So this is one of the technology which is having or gaining very much popularity in green chemistry right now. Second one is the solvent-free technique, which is called the ball milling technique. It is somewhat similar to the similar to the grindstone technique, but it involves small balls in it, and these balls are they are grinded with each other, and along with that, the reactants and reagent they are also mixed. So the particle size of those reactants they are reduced by that, and there is efficient mixing of both the components by which different type of chemical compounds and pharmaceutical important molecules which we call drugs, they can be synthesized. Third one is the very much a technique which is involved in the green chemistry. It's a very popular and recent technique. It has been introduced into the chemistry 10 to 15 years back, which is called very new in terms of chemistry, because chemistry is a 100-year-old subject. It's called the microwave assisted synthesis. Microwave assisted synthesis is the synthesis of the compounds which are biologically relevant by using the microwave radiations. So what they do is they decrease the activation energy required, and the organic compound, they are synthesized in the very much shorter reaction of times. Here the different circles, they represent the type of molecules or the reactions which can be done by using the microwave assisted synthesis. You name a reaction, it can be a cyclization reaction, it can be isomerization reaction, reduction reaction, multi-component reaction, condensation reaction. All the type of chemistry can be performed by using microwaves. And the another one technique which is very famous in green chemistry is the ultrasound promoted synthesis. Basically, ultrasound promoted synthesis is the use of sound waves, very high frequency sound waves, which is involved in the synthesis of many active pharmaceutical ingredient as well as the natural products, bioactive natural products. It decreases the time of the reaction as well as the temperature which is required for the reaction. So both the ways we can save the energy in terms of green chemistry. So that was all about what different type of techniques are right now being used in green chemistry. So now I would like to emphasize on what we are doing in green chemistry in our own lab. First of all, we have synthesized many of the trifluoromethylated heterocycles by using the copper catalyzed trifluoromethylation techniques. So why we have particularly focused on the trifluoromethylation strategies? Because it's a group which is rarely found in the natural products itself, and it can be a good bioisosteer of the CH3 group. It enhances the lipophilicity and metabolic stability of the molecules, and which is a wide known problem in many of the drug discovery processes. So to increase the lipophilicity and metabolic stability, the CF3 group can be introduced in many of the drugs. 3 of them are shown here. Now, the challenges is that it does not occur in the nature. So we have to artificially, or we can say that synthetically, incorporate it into the lab. So if we can devise a technology or a synthetic procedure which can incorporate CF3 through an eco-friendly technique, it would be very good for us. So this is one of the novel synthetic method which we developed. We utilize the widespread dielectrophilic alpha-oxoketene dithioacetals, and first of them, they were halogenated, and those halogens, they were substituted with CF3, and then simple cyclization processes, they were utilized to form the biologically relevant pyrazole derivatives. So what is the green aspect that was involved here? This work was done with somebody else, which involved TMS-CF3 as a reagent. They directly converted H into the CF3, but on the arrow you can see lots of catalyst, 1,10-phenanthroline, silver carbonate, copper hydroxide, and KF are utilized, and then it was cyclized. Our reaction involved only one of the trifluoromethylating reagent, that is MFSDA, which is methyl fluorosulfonyl difluoroacetate. By that, we would able to directly incorporate CF3 from iodine to CF3. We were able to do by bypassing all the hazardous solvents and the catalysts. So that is why it was a green method. And we got completely different regioisomer. It was a very good technique which involved the synthesis of molecules, final trifluoromethylated pyrazole derivatives in 70 to 80% of the yield. Now, this is the structure of all the derivatives that were synthesized, and this work was already published by us. The second methodology or the type of chemistry in which the green aspect was involved was the regioselective synthesis of the half core moiety of a natural product, which is Hardmanin D. So this was the strategy which was involved here. Here you can see is that in the synthesis of compound 13, the green aspect was involved, and this is the half of the Hardmanin D, which is a naturally acting natural product which is anti-inflammatory in nature. So why we were so focused on developing the synthesis of molecule 13? Because here we can see that in the indole, the bromine is attached on the 6th position, which is a very rare one. If you see the chemistry in the laboratory, most of the brominated molecules, they are not attached on the 6th position, they are attached on the 5th position in the indole. But we were able to synthesize a specifically 6th position brominated indole. The type of strategies that were utilized are shown here. First of all, the commercially available 5-methoxyindole, it was the formylated, which is compound A. Now, after the formylation of the 5-methoxyindole, the trifluoromethylation was done, but we were not able to get a single 6 position brominated indole. A mixture of 4, 3 and 3A was obtained, which is again not beneficial for us because we exclusively wanted 9 as our product. So what we did, we rather than formylation, we introduced COCF3 group into the 5-methoxyindole. So after the incorporation of COCF3 into the indole, we were able to get a selective 6 position bromination in the molecule, and it's a classic example of site-directed synthesis. After that, it was hydrolyzed and we were able to get the carboxylic acid. So it was a shorter route. It shows atom economy because the other side products, which are 3 and 3A, they were not required and they were not obtained. And no workup was required because when we did the bromination in the presence of COCF3, we directly got the solid material which was poured into the water and we were able to get the precipitate itself. And it's a scalable synthesis because the overall yield of the reaction was more than 90%. So what we did with this 6-bromo-indole containing molecule, we coupled it with the protected amino acid, and after the various deprotections, the compound 21, which is actually a natural product available in nature, the total synthesis of it was achieved. So these were the optimization reactions. The final coupling reaction was performed in different condition, and finally we were able to get the desired product by the entry number 7. So why I am explaining it here is because the synthesis of 21 can lead to another aspects because it has OH and bromo, which can be readily convertible groups for us. And the synthesis of this anti-inflammatory product, the SR studies can be generated around this molecule by synthesizing 21 in bulk, and that we did. And this work was also published in Senlet in 2022. And this was a green method because we were able to bypass the formylation and the excessive production of the side products that were not desired. Now, another technique or the work which involved the green chemistry involvement in our lab was the ultrasound promoted synthesis of oxazolene derivatives, which involved calcium ferrite nanoparticle as catalyst. So the previous work of the oxazolenes, it reported the synthesis of the oxazolenes by heating them on 70 to 80, 90 degrees centigrade and the use of base also. The similar compounds were synthesized in the absence of base in a very much reduced reaction time, which reduced the reaction time from hours to minutes. So that is what the ultrasound can do in a reaction. It can quickly reduce the reaction time, and the yield of the products also increased and the time also decreased, and which is a simple and straightforward application of green chemistry in the organic chemistry. So another synthesis which involved the green aspect was the glycoside annulated dihydropyrimidinone synthesis. It was a solventless synthesis and it utilized copper ferrite nanomaterials as heterogeneous catalyst. So this is what we did. We first of all, the propargyl beta keto esters were used, transesterification was used, and it was a multi-component reaction which involved the synthesis of dihydropyrimidinone derivatives, and is a perfect example of click chemistry. What is the advantage of this method? It is a green aspect because the reaction was performed using the nanomaterials which can be easily separated and reused up to 3 catalytic cycles. The reaction time was reduced from 3 to 3 hours from 4 hours. And the best thing that come out of this chemistry was the reaction was done under solventless conditions, which is a major achievement in any organic chemistry process, because majority of the solvents which are not alcoholic in nature, they are hazardous in nature. And if you can bypass them and design a procedure which involves the nanomaterials and excludes the solvents, it's far better than other methods which are. And the percentage of yield of the products increase. Individual products yield increase up to 10 to 15%. These are the different type of substrate scopes which are analyzed. We can see that the yield of the products which are obtained through the new methodology, which is the solventless techniques, they are far better than the old compounds which were synthesized. So technically, green chemistry is not actually, if we are completely able to bypass something, even if we are able to reduce it, then actually it is also a green chemistry technique. So these are the derivatives which were synthesized. We can see the beautifully all the electron withdrawing, electron donating, all the groups, they were easily tolerated. The synthesized nanomaterials were characterized by us by XRD, SEMTEM and FTIR data. And all these synthesized compounds, they were further subjected to the DFT studies so that the most stable configurations of the molecules can be identified. Now, another synthesis is the water-based Pictet-Spengler reaction of the tryptophan followed by Buchwald coupling reactions, which involve the synthesis of natural products, stearin A and B, and other beta-carbolin derivatives also. So what was the beauty of this chemistry is, this chemistry involved the synthesis of beta-carbolin intermediates by using water only without bypassing any solvent. And if you are able to achieve any chemical process by utilizing water only, it's tremendous, because water is a very cheap, eco-friendly solvent. It has no hazards and easily available. And all these intermediates were synthesized by using this eco-friendly method. So here we can see that different type of derivatives, 33 which were synthesized, they were coupled with different amines, and the different amide analogs were also synthesized by utilizing this chemistry. And this particular amide derivatives, when they are reprotected, the simple amides were synthesized by utilizing the bromo derivatives. We were able to synthesize stellarins A and B, which are the naturally occurring molecules. Now, another the way towards synthesizing the molecules through green chemistry was using the ultrasound-assisted synthesis of benzodiazepine derivatives using calcium ferrite as a nanomaterials. Now, what was special about this chemistry was the alpha-oxoketene thiothioacetals were utilized by using the orthophenylene diamines, and our work involved the use of ultrasound. The yield were increased from 5 to 10%, and the major achievement was in terms of time. The time that we achieved was a reduction of 3 hours, our all the derivatives were synthesized within a time span of 20 to 45 minutes as compared to the time span of 4 hours of previous reported method. And this is a significant achievement in terms of green chemistry and organic chemistry also, because if you want to synthesize a library of molecules, anyway time is always important. 24 final compounds were synthesized, and this work was recently published in the Sulfur Journal of Sulfur Chemistry. And other than synthesizing the final molecules, the use of the nanocomposite up to multiple cycles was also seen. And we here in the right hand side of the bar diagram, we can see that the catalyst can be utilized up to 3 catalytic cycles. So we were able to achieve a good synthesis with the recyclability of the catalyst also. The molecules which were synthesized, they were further subjected to the DFT calculation studies and the docking studies also. And the molecules which were best docked, they were further evaluated for the antifungal activity also. So these are the different type of molecules which are synthesized. Here you can see that the benzodiazepine derivatives, they were synthesized with a wide substrate scope. The fluoro, chloro, difluoro, bromo, methoxy, all the electron releasing, electron donating groups, they were well tolerated. And the heterocyclic moieties also were well tolerated. In the last line, you can see is that benzofuran, pyridine, thiophene, all this type of heterocyclic scaffolds were synthesized. Now, this is the docking. Two of the compounds, they show best docking studies. And these were further evaluated for the antifungal activities. So what we have got from all these the findings, now the core principles which are leading the driving change in the organic chemistry is prevention. We should always avoid the generation of waste rather than to treat it and find ways to treat in organic chemistry. We should always focus how we can reduce the waste generation in organic chemistry. Second one is the atom economy. Rather than emphasizing on the producing the molecules irrespective of how much conversion was there, we should always maximize the incorporation of all the atoms from reactants into the products. It will automatically reduce the production of the side products. Third method or third aspects that we have looked upon and we should always look upon is design safer chemicals and synthesis so that the toxicity to the humans and environment can be minimized. Because we should always know that the industrial effluents or the chemical waste which is released from the industry or the industrial sector, it always goes to the nature. And we are not the only one which are living in the nature, because other than us, the birds, animals are there. And if the toxicity or the toxic chemicals are released in the environment or in the soil, they affect everyone in the nature. The fourth aspect we have looked upon is the energy efficiency. Because we have conducted the all reactions, we have seen that we have reduced the reaction temperature from 70, 80 or 90 to the room temperature or 30 to 40 temperature, which is an ambient temperature and pressure. And we should always explore these type of technologies where all these type of temperature reduction can be achieved, because it is in terms of energy efficiency that we are going to achieve by using this. And another aspect we have looked upon is use renewable feedstocks. For example, the nanoparticles that we have utilized in our reaction, they can be utilized up to 3 catalytic cycles, which are in turn reduces their overall use, and they will be synthesized in lesser amount. And last one, which I have always emphasized, and we should, as an organic chemist, we should use catalyst to reduce waste and energy consumption. That again, if a catalyst can be regenerated up to 3 to 5 cycles, it's a good catalyst. And we should always keep in mind that we have to design for degradation. Anything which is not degradable in organic chemistry is always a hazard for us, for environment, for everyone living with us in the environment. So ensure the products break down into the harmless substances after use. And this can be achieved by using a solventless method, by using eco-friendly reactions, by using eco-friendly enzymatic technologies, by using chemicals of the biological origin, so that we can always produce a newer chemicals or the chemical entities which are always required in the drug discovery processes, but the synthesis side by side is also safe. So for this, I would like to conclude my talk and thank you all.